On the left, we have one way to represent an ethane molecule. The only problem in this drawing is that it doesn't give us much information of what ethane looks like in 3 dimensions. On the right is another drawing of ethane molecule. This drawing gives us more information. This is a wedge and dash drawing showing basically 2 hydrogens. So showing over here we have 2 hydrogens. These are the 2 hydrogens. These 2 hydrogens are in plane of each carbon. One hydrogen showing as a wedge, and as we mentioned last time, the wedge is a representation of a bond which is coming at you in space. So it's coming towards you, it's in front. And then one hydrogen, which is represented as a dash, which is behind, it means that it's going away from you in space or into the plane of the page. The wedge in the dash represents one conformation of ethane though. Conformations are different arrangements of atoms that result in bond rotation. We know that there is a free rotation around the carbon single bond carbon, and this wedge and dash representation that you see over there, this is called the staggered conformation of ethane. But if we rotate around the carbon, single bond carbon, we will get different arrangement of the atoms, and therefore we will get different conformations. The easiest way normally to see the model is to see these types of conformations is to look at the model set. So up next, I have a small video for you to watch with a model set of ethane where we rotate around the carbon-carbon bond, so we can see the different conformations. Now in the video we will make this set of hydrogens in here that belong to the carbon which is in front towards you. So this carbon is going to be in front. So the set of hydrogens that belong to it, we're going to make them green. And then the set of the hydrogens that belong to the carbon at the back, so this is going to be the back carbon, these we're going to make them white. So let's go ahead and watch the video and look at the different conformations of alkanes.
Here we have the staggered conformation of ethane, looking at it from a wedge and dash perspective. If we rotate this a little bit, we'll see the staggered conformation of ethane from a sawhorse perspective. If we sight down the carbon-carbon bond, we'll see the third way of looking at this molecule, and this is called a Newman projection. If I take one of these hydrogens here and I rotate it, so I'm keeping the back carbon stationary and I'm rotating the front carbon, every time I rotate this, that represents a different conformation of the ethane molecule. So there are many, many possible conformations in theory. I rotate back to the original position here, so this is the Newman projection where we just were. The other conformation that we really care about for ethane is what's called the eclipsed conformation. So I just rotated the green hydrogens so they're in front or eclipsing the white hydrogens in the back. So this is the eclipsed conformation as a Newman projection. I could turn this a little bit so we could see what an eclipsed conformation looks like as a sawhorse, from a sawhorse view. And then finally, I can turn it a little bit so we can see the eclipsed conformation from a wedge and dash perspective. Now that we've seen the video, let's look at 3 ways to represent the staggered conformation of ethane. And we'll start with the wedge and dash drawing. So you could see that this hydrogen, this carbon, and this hydrogen are all in the same plane. So they're all in the same plane here, which is why all these bonds are drawn as straight lines in our wedge and dash drawing. If we look at this carbon on the left, right, we know that there is a hydrogen in green coming out at us in space, a hydrogen in green going away from us in space, and then this hydrogen which is in the plane of the page. For the hydrogens in white, this hydrogen is in the plane of the page, this one's coming out at us in space, and then we have one going away from us in space. And it's pretty easy to see that in the picture here. So we're just going to match the drawings to the pictures. Our next way to represent the staggered conformation is what's called a sawhorse drawing. So for this sawhorse drawing, this carbon right here is this carbon, and it has 3 hydrogens in green attached to it. So this is a hydrogen in green, and in green. So we also have this carbon-carbon bond. So that's this bond here on our sawhorse drawing. And then finally for this carbon in the back, this is the one that has hydrogens in white. So these are the 3 hydrogens in white. If we look down that carbon-carbon bond, if we look down this axis right here, so if you put your eye, imagine putting your eye right here, so here's the eye, and you look down this axis, you will see the Newman projection, just like we saw in the video. And so this dot, this point here, represents the front carbon. That's this carbon right here. So let me go ahead and write that down. So this point represents the front carbon. And the front carbon is bonded to our hydrogens in green. So this would be a hydrogen in green, so is this one, and so is this one. The front carbon blocks the carbon in the back. You can't see the carbon in the back in this drawing, but we know it's there, and we have to represent it somehow. So in a Newman projection, it's this circle. It's this circle back here that represents the back carbon. So this is the back carbon, this circle. Let me write that down. The circle is the back carbon, even though we can't see it when you actually have the model in front of you. And the back carbon is the one that has the hydrogens in white. So this should be a hydrogen in white, so is this one, and so is this one. So here you can see the hydrogens in white back here. And you know they're attached to a carbon, but you can't see it because the front carbon is blocking it. So let's talk a little bit more about Newman projections. We can talk about the angle between this hydrogen in white and this hydrogen in green. So think about the angle between these. It's 60 degrees. So we have a 60-degree angle between these 2 hydrogens. So I could write it down here too. So 60 degrees. This angle is called the dihedral angle or the torsional angle. So I'll write those down. So you could call this the dihedral angle, or you could also call it the torsional angle. Let me write that down here too. So torsional angle, or you could also call it the torsion angle. And this angle between the hydrogens will be important when you're talking about conformations. Here the angle is 60 degrees, which means that these hydrogens are not right on top of each other. There's space between these hydrogens on the Newman projection. The green hydrogens are staggered compared to the white hydrogens. So if you go around, you can see that there's space between all of these, and that's why we call this the staggered conformation of ethane. And finally, let's look at the other important conformation of ethane, which is the eclipsed conformation. And we'll start with the wedge and dash drawing. So we have this hydrogen, this carbon, and this hydrogen. These are all in the same plane. So I draw this line here, and we can see these bonds are all in the same plane up here on my wedge and dash drawing. For this carbon on the left, we can see that we have a hydrogen in green coming out at us, right? So here's your hydrogen in green coming out at you, a hydrogen in green going away from you back here, and then this hydrogen in the plane of the page. For the hydrogens in white, this hydrogen is in the plane of the page, right? This hydrogen is coming out at us in space, and this hydrogen is going away from us in space. For the sawhorse drawings, let's move on to here. This carbon is the front carbon, so that's this carbon right here, the one that's bonded to the 3 hydrogens in green. So let me highlight those. So we have one hydrogen, this one right here is going up, so that's our hydrogen in green going up. This hydrogen over here is going down a little bit to the right, and this hydrogen is going down and to the left. And then we have the carbon-carbon bond, so let me draw that in here. So here's our carbon-carbon bond. I made it much longer up here just so the atoms wouldn't interfere with each other on our sawhorse drawing. And then we get to the carbon in the back. So here's the carbon in the back, which is bonded to 3 hydrogens, and I made these the hydrogens in white. So here's 1, 2, and 3. So here are the hydrogens in white on the picture. Finally, we get to the Newman projection for the eclipsed conformation. And remember, the Newman projection is what we would see if we stare down the carbon-carbon bond. So if we sight down this carbon-carbon bond, if we put our eye right here on our sawhorse projection and we stare down the carbon-carbon bond, we see this for our Newman projection. Right, first we see this point here representing the front carbon. So that point is the front carbon on our Newman projection. And the front carbon is bonded to the hydrogens in green. So here's 1, 2, and 3. So up here, 1, 2, and 3. So this would be the bonds. This represents the bonds of that front carbon to those hydrogens. The back carbon is pretty difficult to see, but we know that the circle represents the back carbon. Right, the front carbon is in the way. I'm not sure if you might be able to see a tiny bit of the back carbon here, but the back carbon should be blocked by the front carbon. The back carbon, we know, has our hydrogens in white. So here are the 3 hydrogens in white. So back here, you can just barely see them. You can just barely see them poking out. This time, when you think about the angle between your hydrogens, this time your dihedral or your torsional angle is 0 degrees, right? Think about this hydrogen being perfectly upright and the hydrogen in the back being perfectly upright. So the angle between those is 0. So your dihedral angle is 0 degrees here for the eclipsed conformation. The green hydrogens are eclipsing the white hydrogens. So that's why we call this the eclipse conformation.
Okay, so as you saw in the video, there are 2 types of conformations for a carbon single bond carbon, and these conformations are named either an eclipse or a staggered conformation. It's the way how the bonds are arranged. So in an eclipse conformation, as you can see, all the CH bonds, they are directly aligned with each other. So the angle between them, the dihedral angle between them is going to be 0. So the angle between these 2 over here, these 2 are on top of each other. These 2 hydrogens are on top of each other. These 2 hydrogens are on top of each other, and these 2 hydrogens are on top of each other. So there is no angle actually between them. The angle is going to be 0. And then you have the staggered conformation. The staggered conformation is a conformation where the CH bonds on one carbon. So if we're working with the CH bond on one carbon in here, it's going to bisect the C and the CCH bonds. These are the hydrogen bonds on the adjacent carbon, making an angle between these 2 to be a 60-degree angle. So rotating the atoms on one carbon by 60 degrees, you can go from an eclipse to a staggered conformation. Having a molecular model with you will help you with that, to even to see it and to be able to view it easily. The angle, as we mentioned, that separate a bond on one atom from a bond on the adjacent atom, this is called a dihedral angle. Another name for it is a torsional angle. It's a torsional angle. There's an L in there. So for ethane in the staggered conformation, as you can see over here, the dihedral angle between the 2 CHs, this is going to be a 60-degree angle. If you rotate a 60 degrees, you can go to an eclipse conformation. So the point is, you can go from one type of conformation to the other by rotation. Remember that you have a free rotation around the carbon single bond carbon, and the rotation is going to be a full circle. So it's going to be at 360 degrees. So this means that the angle between the dihedral angle between every carbon and the CH, that's going to be 60. So the angle between these 2 bonds is going to be 60 degrees. This is 60, this is another 60, this is another 60, and that is another 60 for a full rotation of 360 degrees. To represent this on paper, we simply draw a Newman projection to represent the staggered and the eclipse conformation. So what we have here is the staggered conformation. Now with the staggered conformation, what I'm saying is this carbon to be in front. So this is my carbon being in front. If I am looking here at this axis, then I'm going to see this carbon in front and I'm going to see the carbon at the back. I won't see the bond that separates the 2 carbons. I won't see that sigma bond. But I would see the carbon in front and then I would see the carbon at the back. This is why when you draw a Newman projection is always between 2 carbons. So I have to specify, if I have a long chain, if I have a long alkane chain, I have to specify along which sigma bond I want you to draw the Newman projection. So I have to tell you, I want you to draw the Newman projection around carbon 2, carbon 3, and carbon 4. So this is why you would know that the Newman projection is basically around the sigma bond. So this makes you can easily draw the Newman projection this way by either looking from down from carbon 3, having carbon 3 in front. This means that carbon 4 is going to be behind, or you can look through carbon 4, and carbon 4 now is going to be in front and carbon 3 is going to be behind. The way that you look at it really doesn't matter. But every time you draw it, you're going to draw your eclipse and your staggered conformations. The number of conformations basically depends on the alkane chain and how many carbons are there in the chain. So to represent the Newman projection as in the video, you start by pointing the carbon in front. The carbon in front is basically represented by a point or a dot, and the carbon behind is represented by a circle. And then after you do this, you simply draw the bonds that you see in your staggered conformation. So here in the staggered conformation for the carbon in front, so this is going to be my carbon in front in here. And then the carbon at the back, I'm going to make it green. So that carbon at the back in here, this is going to be green. And that will be represented by the circle. So the carbon in front has, so the carbon in front has basically the two hydrogens, has all of these three hydrogens pointing. So this is going to be my hydrogen pointing in plane. Okay. So this is going to be my hydrogen, and then I'm going to have a hydrogen pointing on the side, and then I'm going to have another hydrogen on the other side. Okay. One more thing that I want to say, that any groups pointing on this side of the Newman projection, these we're going to label them in front. This means that if you have a wedge and dash structure and you have a hydrogen in front, then it should go on the side. Any groups that are pointing behind are going to go on that side. And any groups that are pointing in plane are going to go on this vertical line. Okay, so these hydrogens in here, they represent the groups that are pointing in plane. Okay. So with this said, there are only two conformations for ethanes. So we're gonna check the conformation for a 2-carbon chain, 3-carbon chain, and 4-carbon chain, and we're gonna see. So for ethanes, since ethane have hydrogens in there, all the hydrogens are gonna be the same. We have 2 in front, 2 at the back, and 2 in plane. Then we're going to end up having only 2 conformations, the eclipse and the staggered conformation. For the staggered conformation, this is the staggered conformation of the hydrogens. This is the staggered conformation of ethane, representing the hydrogens having a 60-degree dihedral angle. If you go ahead and you rotate another 60, now when we do the rotation, this is what we do. Normally we fix the carbon in any of the carbons, either the carbon in front or the carbon at the back. Here they fix the carbon at the back. To do a rotation, you need to fix a carbon. So here they fix the carbon at the back. So as you can see, the carbon at the back stays the same. The carbon in front is the one that they rotated. That carbon in here, they rotated. Rotation can be either clockwise or counterclockwise, whatever you want. Here I am going with clockwise. Remember that between the two lines, this is a 60-degree. So you're going 60 degrees, 60 degrees, 60 degrees, 60, 60, and 60. This is a full rotation. So if I want to rotate 60 degrees to go from staggered to eclipse, here's what's going to happen. See that hydrogen? That hydrogen will basically align with this hydrogen here. So I'm going to represent it like this. And this hydrogen will align with this hydrogen here because I am rotating actually 60 degrees. And this hydrogen will align with this hydrogen, so I'm going to represent it like that. And this shows the eclipse conformation with a zero dihedral angle. This is how I represent a Newman projection for staggered, and this is how I represent it as a sawhorse. As a sawhorse, this is just the molecular model with no circles in there. I am basically looking and viewing the carbon in front, and I'm viewing the carbon at the back. This is a sawhorse representation. To go from the Newman to the sawhorse, it's simply straightforward. You take away the circle, and whatever bonds you see, you just draw. So here I am seeing the hydrogen in front, you draw it. I'm seeing this hydrogen to be at the back, I'm drawing that hydrogen, and I'm seeing one hydrogen in plane, I draw it down. Then for the carbon at the back, I am seeing a hydrogen in plane up, so I'm going to draw it. I'm seeing a hydrogen here at the back, I'm drawing that, and I'm seeing this hydrogen in front, and I'm drawing it as I'm seeing it. The angle, the dihedral angle between these two hydrogens here is 60 degrees. So they are pretty much far away from each other. With respect to the eclipse conformation, if I want to change it into a sawhorse, remember that with eclipse, all bonds, they align with each other. The angle between them is zero, so there is a lot of strain in there. There's a lot of repulsion in this case, and we will talk about the types of interactions that you have between the two hydrogens that are eclipsing each other's. So you have here the sawhorse, and for the sawhorse, you just draw it as you see it. And I'm seeing here that this is the carbon in front. So this is going to be the carbon in front. The carbon in front has the hydrogens pointing up, and then two hydrogens are going to be on the sides. And then the carbon at the back, same thing, the hydrogens are aligning with each other. So basically these two have a 0 degree dihedral angle. They are basically on top of each other, and these two hydrogens are on top of each other. They align, and these two hydrogens, they align, and there is a 0 degree dihedral angle in them. So with ethane, you can simply convert, as in any conformation. When you want to go from one type of conformation to the other, from the staggered to the eclipse, you can easily go at room temperature from staggered to eclipse. You are simply rotating around the carbon, single bond carbon. This is what you're doing. You're going from staggered, you're rotating 60 degrees, and you are forming the eclipse conformation. Now, as I mentioned, when you do a rotation, normally you fix one carbon. It doesn't matter which carbon you fix. Here I'm fixing this carbon, so it stays the same. And I am rotating the one which is in front in this case, if I am looking in this direction along this axis. So I'm rotating this carbon in here, rotating this carbon simply is going to make the eclipse conformation. Now, which one is more stable? The one that has low energy is the one which is more stable. So normally when we talk about stability, stability means a structure that has low energy, and a structure that has low energy should have a low electron repulsion between the bonds. So the less the repulsion between the bonds, the more stable the molecule is, because its energy is going to be less. And this is what we are looking for. We're looking for the bonds to be the farthest away from each other, so that we have less electron repulsion between the bonds to make the molecule more stable. This means that always staggered is going to be more stable than the eclipse conformation. So for ethane, we said that we have two types of conformations. We have the staggered and we have the eclipse conformation. So the eclipse conformation over here, this is going to be the eclipse conformation for ethane. And this is going to be the staggered conformation of ethane. And we can go from staggered, this is staggered, okay. So we can go from eclipse to staggered by simply rotating 60 degrees. So every 60 degrees is going to give me a staggered, and then another 60 is going to give me an eclipse, and then another 60 is going to give me a staggered. So this is why I have an alternation between eclipse staggered, eclipse staggered, eclipse staggered. Now for ethane, all the eclipse conformations are going to be the same, having the same energy, and all the staggered conformations are going to have the same energy. Reason why? Because all the groups are the same. When I ask you to plot the energy diagram of ethane or any other alkane, the energy diagram normally hosts all the Newman projections, all the conformations of between the carbon single bond carbon. So between the carbon single bond carbon, I have two of them only, and these keep alternating in there. So what you need to do is basically choose a dihedral angle, a certain dihedral angle. Here I'm locating my dihedral angle between these two hydrogens over here. And I am fixing one carbon, and I am rotating 60 and seeing how the conformation changes as a result of the rotation. So between these two hydrogens, I started with a 0 dihedral angle. And the 0 dihedral angle, I started with the eclipse conformation. The eclipse conformation, because I do have eclipsing of the bonds, all of these bonds align, the energy is going to be very, very high. So the energy of the structure is going to be high. Then going 60 degrees, now I have a 60 degree between the two hydrogens. Again, you fix the carbon at the back. In this case, I'm fixing the carbon at the back. I'm rotating the carbon in front. So rotating the carbon in front will make this hydrogen here. Okay, so it will be here, and this hydrogen is going to be here. This is going to be their 60, and then this hydrogen here is going to be here, so it's going to be another 60. That is going to be the staggered conformation, and now the angle between these two hydrogens is 60. Again, the dihedral angle axis is just a representation of the dihedral angle between the two groups that you point at. So normally you choose the groups that you want to plot their dihedral angle and plot their energy graph or energy diagram. Going another 60, so so now I'm having 120. So going another 60 will make this hydrogen here, so going eclipse now. And then this hydrogen is going to be here, and this hydrogen is going to be there. So going now eclipse, so notice, eclipse, staggered, and so forth. Going another 60, that is going to make the bond angle between the two hydrogens 180 in that case. And I'm going to be back to the staggered now. Since all the staggered, they are the same, then they're going to have the same energy, and they're going to have low energy because the bonds are far away from each other. And since all the eclipses are going to be the same, then they're going to have the same energy, and their energy is going to be higher because the hydrogens basically align with each other. So what you're going to end up basically getting is you're going to end up having your energy diagram that looks like this. This is going to be your energy diagram in there. Now normally the energy difference between the staggered and the eclipse conformation, we call it torsional energy. This is called a torsional energy. There are certain problems on Top Hat that I posted with their key. These are extra problems that I ask you calculate the torsional energy of the structure, and the torsional energy is basically the energy difference between the staggered and the eclipse. So you need to calculate the energy of the staggered, you need to calculate the energy of the eclipse, and then subtract them from each other to get the torsional energy. Another name for the torsional energy is the barrier of rotation. So it's either torsional energy, or we call it the barrier of rotation. So any one of those, barrier of rotation, any one of those is the same basically idea. And as we mentioned over here, the torsional strain normally is increased when you have eclipsing of the bonds. So when the bonds eclipse each other, they align, you have a torsional strain. Torsional is basically a method to explain that bonds align with each other. Torsional means eclipse. So a torsional strain occurs whenever you have eclipsing of the bonds. So every time you have an eclipse conformation, you have a torsional strain. And the torsional strain will be for the bonds that are aligning with each other. So these two CH bonds, they are eclipsing each other. So there's a certain torsional strain in there. There's a certain energy that basically is represented for these two eclipsing of the bonds. Same thing, there's a torsional strain between these two bonds. There's a torsional strain between these two bonds in there. Later on, I'll show you a table, and this table will represent the torsional strain of different molecules when they are basically aligning with each other and their corresponding energy. Now for propane. For propane, we have a chain of 3 carbons in there. And as I mentioned, I need to specify exactly which carbon-carbon single bond I want you to draw the Newman projection along. So here I am locating this carbon-carbon single bond over here that I want you to draw the Newman projection around. I'm going to label this carbon 1 and this is carbon number 2 over there. Okay? Now, there's a rule whenever you want to draw a Newman projection. Normally, the long carbon chain has to be along the vertical line. That makes it easy to spot when you have a Newman projection and I ask you, go ahead and change that into a structural formula. So you can look down or look along this line and say that, you know what, this Newman projection has that much carbons because this is going to be the long carbon chain. Now, right now, my long carbon chain is a carbon, is a CH3 and 2 carbons here. 1 carbon in front and the other carbon which is behind represented as a circle. So I know that this is going to be a 3 carbon chain. Okay? So let's go ahead and represent the propane in a form of a staggered and eclipse conformation. So for a staggered conformation over there, as you see, this is going to be the carbon. So if I make this carbon in front, I am looking along this line over here. So I am seeing this carbon to be in front. If I want to draw it in the Newman projection, that's going to be in front. It has 3 hydrogens. The carbon at the back has 2 hydrogens and it has a CH3 over here. And as I mentioned, always make sure that the big groups are on the vertical line as much as you can, okay? And the carbon chain is along the vertical line. Now, this is the staggered conformation. If I want it to be an eclipse conformation, then I'm going to fix the carbon at the back. You can, again, fix the carbon in front. It doesn't matter. But fix one carbon, rotate the other carbon. When you do your rotation, do it for all the conformations in one direction. So if you chose to rotate clockwise, make sure that you rotate clockwise for all the conformations. I'm fixing the one at the back, rotating the one in front. So rotating 60 degrees. So now I am going 60 degrees. Rotating 60 degrees, then this hydrogen is going to be eclipsing the CH3. I'm going to show it like this. So the dihedral angle between these two is going to be 0. And this hydrogen is going to be eclipsing this hydrogen here. So again, it's going to be 0. And this hydrogen is going to be eclipsing this hydrogen here. So again, the dihedral angle is going to be 0 because the bonds are aligning with each other. You can easily change the Newman projection into a sawhorse. As you see it, you just draw it, but now you reveal the carbons. You have the carbon at the back, the carbon in front, and take away the circle, and then draw it as you see it. Same thing for the staggered sawhorse conformation. If I'm comparing between these two, which one has a higher energy? Of course, this guy over here, because here I do have eclipsing of the bonds. See how many bonds I have eclipsing each other. I have 2 hydrogen bonds that are eclipsed. And then I have a 1 hydrogen CH3 bond that are eclipsing each other. So this is going to be my torsional strain in this case. Remember, we said torsional strain is basically the interaction that happens between the bonds when they are eclipsing each other. So I have that much torsional strain in this case. So if I compare the staggered conformation to the eclipse conformation is going to have a higher energy, so it's going to be the least stable. The higher the energy, the less stable the compound is. They go inversely proportional to each other. So now if I want to draw the energy diagram of propane, of the Newman projections of propane, or so in this case propane is going to have the eclipse and the staggered conformation, and it's going to have only two of them. It's not going to have more than that, because again the groups are the same, and here I have the hydrogens to be the same. So we're going to start with, here in this diagram, I'm starting with the dihedral angle between the hydrogen and the CH3. You can locate the dihedral angle between these two hydrogens and then rotate and see how it behaves. It's going to give you the same thing, but I went with the hydrogen and the CH3. So having an eclipse conformation, eclipse is going to have a high energy. So this is the eclipse conformation, high energy with a zero dihedral angle. Then if you rotate 60 degrees, here they're fixing the carbon at the back, they're rotating the one in front. 60 degrees will bring this hydrogen here. This hydrogen is going to be here, and this hydrogen is going to be here. So you're going to end up having the staggered conformation. Now with the staggered conformation, the angle between the hydrogen and the CH3 is 60. This is far away from each other. Hydrogen is a small atom in here, so there is no interaction between the hydrogen and the CH3. So this is why the staggered conformation has a low energy than the eclipse conformation. And then you go another 60 degrees. So another 60 degrees will make the angle between the hydrogen and the CH3, the total angle, to be 120 degrees. You always go from staggered to eclipse by rotating 60. So if I go another 60 degrees, then I'm going to go with the staggered conformation, and the staggered conformation basically is going to look like this. Now the back, I didn't do anything to it, so I'm just going to leave it like that. With respect to the front carbon, I am rotating 60 degree this way over here. So now this hydrogen is going to basically be, okay, this hydrogen is going to be here, this hydrogen is going to be there, and then this hydrogen is going to be over here. So I'm going to end up having this structure. So again, as you can see, I'm going from eclipse to staggered, and then eclipse, and then stagger. I'm going to keep doing this until I rotate a full circle in there. So I'm going to end up having my energy diagram alternation between eclipse and staggered conformation. So this is the staggered, and then you have the eclipse, you have the staggered. All the staggereds are the same, so they have the same energy. All the eclipses are the same, they have the same energy. Now you start seeing more conformations when the number of carbons increase. So here I have a butane. A butane is a chain of 4 carbons, and I am drawing the Newman projection along, okay, along carbon 2 and carbon 3. So I am viewing this way over here. So carbon number 2 is going to be in front, and carbon number 3 is going to be at the back. So let's start. And as I mentioned over here, when you draw the Newman projection, make sure that the carbon chain is along the vertical line, so that it's easy to spot how many carbons you have in your parent chain. So here I have 1, 2, 3, and then 4. So my chain is made up of 4 carbons. So let's go ahead and put the substituents around every carbon. On the carbon in front, what I have is 2 hydrogens. These are my 2 hydrogens. Okay. Now the 2 hydrogens, one hydrogen is going to be in front, the other one is going to be at the back, and then I have I do have basically a CH3 over here. Do you see that CH3? That CH3 is going to be in plane. That CH3, I'm going to put it on the vertical line. Okay, so this is going to be my carbon in front. I'm going to put it on the vertical line. The hydrogen in front, I'm going to put it on the side. The hydrogen at the back, I'm going to put it at this side over here. Okay, we agreed that this side is the front, this side is at the back, and this side is going to be in plane. And always in plane is going to host your longest carbon chain. So if you have any carbons, please make sure to go ahead and put them on the vertical line. And then we have the, now carbon 2 is connected to carbon 3. You cannot see carbon 3. So carbon 3 will be represented by a circle. And on carbon 3, what do I have? I have a CH3, so this is going to be my CH3 here. And then again, I have a hydrogen in front. And then I have my hydrogen at the back over here, okay? So I have my hydrogen in front, and I have my hydrogen at the back. So this is going to be my hydrogen in front, and that's going to be my hydrogen at the back. Now, these two hydrogens, the angle between them, these two hydrogens are the hydrogens in front. They are not eclipsing each other. If you build the molecular model, you're going to see that these two hydrogens have a 60-degree angle between them. And these two hydrogens at the back are going to have a 60-degree angle between them too. And there's a 60-degree angle between every single one of these atoms in there. Okay? So there's a 60-degree angle. This is a full rotation of 360 degrees. So now let's go ahead and start rotating. We're going to start rotating until we reach the same structure that we started with. Fix one carbon, rotate the other. I'm fixing here the carbon in front, and I'm rotating the carbon at the back. So rotating the carbon at the back is going to make the CH3 here 60. So this is going to be my 60. So I'm going from staggered to eclipse. This is going to be my 60 over here. And then rotating another 60 degree. Remember, we've went with the clockwise direction. So we're going to keep continuing rotation in the same direction. 60 degrees. So now the CH3 is going to be here. That hydrogen is going to be there. I'm going to end up having my eclipse conformation. Rotating another 60 degrees. And as I mentioned, I am fixing the carbon in front. So the one in front is fixed, and the one at the back is the one that is basically rotating. So the one at the back here, rotating another 60, I'm going to have my CH3s directly aligning with each other. Imagine how much energy this structure has. This is basically having all of these CH3, these two CH3s, they are on top of each other. These are big groups. These are the biggest group in the structure, and they are on top of each other. And then I rotate another 60. I'm going to end up having my staggered conformation, and then another 60 eclipse, and then another 60 back to whatever I started. You've noticed over here that there are different types of eclipse conformations, different types of staggered conformations. So let's go ahead and name them, because naming in this case here, it's very important. And this is what we're going to use to name the different structures of, or the different conformations of alkanes. If you have the two biggest groups, the farthest away from each other, 180 degrees away from each other. Now the two big groups can be any big groups in there. It can be bромines, any halogens, can be R groups, the CH3s. If you have them away from each other 180 degrees, this is called an anti-conformation. The anti-conformation, since the biggest groups are very far away from each other, there is no sort of electron interaction between them. So this means that the energy of this structure is really low. This means that the stability is very, very high. So for the staggered anti-conformation, this is the most stable conformation. This is the most stable conformation. Okay? Now, going to the eclipse over there, I do have torsional strain because I do have one hydrogen-hydrogen eclipse bond. I do have one hydrogen CH3 eclipsing each other, or basically two hydrogen CH3s eclipsing each other. So here I have a torsional strain. So the eclipse conformation is going to be higher in energy than the anti. The anti is going to be the most stable. This is the lowest energy. Going 60 degrees, I'm going to end up having staggered. But this is staggered over here is different than this is staggered over there. The staggered here has the CH3s very far away from each other, no sort of interaction between them, 180 degrees. But the staggered here, no, it has the CH3s that are 60 degrees away from each other. There's a name that we give for such a structure which we call gauche. So gauche is basically a staggered conformation where the two big groups are 60 degrees away from each other. Now, being 60 degrees away from each other is going to allow them to interact with each other. So this is going to lower the energy a little bit of the structure. And then we have the eclipse, but see, this eclipse conformation is different than this one because this here has the two big groups. They are directly aligning with each other. So I'm going to call this a fully eclipse. So I'm going to call this a fully eclipse conformation. This is called fully eclipse. So fully eclipse is whenever the two big groups, they are directly aligned with each other. And in this case, this eclipse conformation is going to have the highest energy. It's going to have the highest energy. Okay? So it's going to have the highest energy. You're going to keep rotating. You're going to end up having staggered. So I'm going to end up having staggered. But again, I went with the gauche. So the gauches are going to have the same energy here. Rotate another 60, I'm going to have the eclipse. The eclipses are going to have the same energy. So 2 and 6 will have the same energy. 3 and 5 will have the same energy when I plot them on the graph. And then 1 is going to be the most stable with the lowest energy. And then 4, structure 4 or conformation 4 is going to have the highest energy in that case. Here I'm just defining the term anti and the term gauche and showing that with gauche you have the CH3s that are 60 degrees away from each other. So these two, they are close to each other and they interact with each other, normally increasing the energy of the structure. With the anti, the largest groups are 180 degrees away from each other. They have no sort of interaction with each other, so the energy of the structure is going to basically decrease in this case, causing the structure to be more stable. The two types of strain that affect the energy of the structure are steric and torsional. Just to define these terms before plotting the energy diagram of the structure. So before plotting the energy diagram of the butane, to define, the torsional strain happens whenever you have eclipsing of the bonds. Steric strain. Now steric strain whenever you have two large groups close to each other. They can be either eclipsing or they can be gauche. Then the type of strain is going to be a steric strain. So if you look here, what I have is a Newman projection for the two CH3s that are gauche with respect to each other. So these two CH3s over here, they are going to have some sort of a steric strain, which is caused by the van der Waals repulsion. So in this case, I'm going to end up having my steric strain. So for the gauche, I have only my steric strain. But if I have an eclipse conformation, so for the fully eclipse, if I have an eclipse conformation, let's say if I have an eclipse over there, this is going to be a fully eclipse where the two CH3s align with each other. Then I'm going to end up having a torsional strain because of the bonds that are eclipsing with each other. And I'm going to end up having an additional type of strain, which is a steric strain, because the two CH3s are close to each other. So steric is a term we use whenever we have groups, big groups that are close to each other. They can be close either 60 degrees apart or they can be 0 degrees apart. And then the term torsional is basically a term that we use whenever we have eclipsing of the bonds. So every time we have an eclipse bond, we have a torsional strain. This is the table that I've been talking about. And this table, you are allowed to have it in the exam. This table shows you the energy values. We report normally the energy values of the eclipse and the gauche and the steric and the torsional eclipse for the CH3s in terms of 2 units. We can either report it in terms of kilocalories per mole, or I've included another table for you over here where normally we report it in terms of kilojoules per mole. Whatever unit you want to use, you can go ahead and use that unit, and both are gonna lead you to basically the same answer. It's just a unit difference in that case. When I ask you calculate the barrier to rotation, or another name for it, the torsional energy. Okay, so if I ask you to rotate the barrier to rotation, or another name to it, the torsional energy, then in that case, all what you need to do is use this table and calculate the energy difference, or the energy of the staggered, the energy of the eclipse, subtract them from each other, and see what number you get, and that is going to be the barrier to rotation, which is the energy difference between the lowest and the highest energy conformations. Okay, let me have this first over here before. So in this slide over here, we are drawing the energy diagram of a butane. See, we have different different conformations of butane, starting from the anti. Anti is the lowest energy conformation, and then rotation 60 degrees. So here I'm starting with the dihedral angle 180. Again, the x-axis, you can start with whatever dihedral angle you wish to start with. Here I am basically locating the angle between the two CH3s, and seeing how it changes as I do the rotation. So I'm going from 180, then I rotate another 60, so here I'm going 120 now. It's going to be 120 between the two CH3s, and then it's going to be a 60 degree, and then it's going to be a 0. 0 is fully eclipsed. See how much the energy is that structure correspond to, or that conformation corresponds to. It's the highest energy. And then you have the staggered, you have the eclipse, and then you have the anti. Always remember that the staggered is low energy than the eclipse. The staggered here in this case have a Gauss interaction. It does have a Gauss interaction in here, but the eclipse does have eclipsing. It has a torsional energy here. Here I have a steric strain. Here I have torsional strain. The torsional strain is higher in energy than the steric strain. We can easily calculate that. So let's go ahead and identify the alkanes corresponding to each of the drawing shown. This is basically a practice. If I give you a Newman projection and ask you, just go ahead and draw the alkane structure in there, the structural formula or the condensed formula, you can easily change from a Newman projection to the alkane. So if you look here, this is what we're looking at. We're looking at the carbon in front. So here I know that Newman projection is between two carbons. So I'm going to start from this carbon over here. So this is going to be my carbon. It's going to be my in front carbon. I know that in front carbon is connected to the carbon at the back that I cannot see. This is represented by a circle. So every Newman projection has two carbons, and draw these two carbons. And then go ahead and draw the substituents around each of the carbons. So I know that this carbon has 3 hydrogens around it. So I'm just going to go ahead and draw the 3 hydrogens. So I'm having a hydrogen here, I am having a hydrogen here, and I am having a hydrogen in here. Okay. And then the carbon at the back has a CH3, so I'm having a CH3 over here. This is my CH3. And then it has a hydrogen here, and it has a hydrogen in there. So right now what I did is I drew my staggered conformation. They're not asking me about the staggered conformation. They are basically asking me about the alkane. So I can simply change this into the alkane. So drawing the structure, that is going to be a CH3. This is a CH3. This is going to be a CH2. And this is going to be a CH3. But drawing the staggered conformation, it's an easy transition in there so that I can read it down and write the structure. So with the sawhorse, I can read it directly from the sawhorse in here. So I am having a CH3. So for B, the alkane structure is a CH3. That CH3 is connected to a CH2. So I'm having a CH2 over here. And then I'm having a CH2 over there. And then I'm having a CH3. So this is basically a sawhorse of butane. So you can simply draw it's a chain. And then C and D, they are representations of wedge and dash. Let's see what type of alkanes. This is a butane over here. What type of alkane you have? So you have a CH3, and that CH3 is connected to a CH2. This is my CH2 over there, and that CH2 is connected to a CH. And on the CH, I have my isopropyl group. This is going to be my CH3, and that is going to be my CH3. So whenever I want to name this, CH3, CH2, CH, and 2 CH3s, that is going to be 2-methyl-butane. Okay, this is carbon 1, this is carbon 2, this is my 4-carbon chain. This is the bond line structure, so just go ahead and give it a name. Choose the longest carbon chain, so I have 1, 2, 3, and 4. This is my longest, so it's going to be butane. And then naming it, I'm going to start numbering from this side, because on this side I have closer to substituents rather than one substituent on that side. Then it's going to be 2, 2, and 3. Okay, so 2, 2, 3, trimethyl, and then 1, 2, 3, and 4. This is going to be butane. 2, 2, 3, trimethyl butane. Another example is draw the Newman projection of 2-methyl-butane. Now, when I ask you something like this, the first thing that I want you to do is draw the structure. Okay, draw the structure, make it easy on you. I have to locate along which carbon single bond I want the Newman projection to be. Here I want it to be between carbon 2 and carbon 3. This is carbon 1 because I'm naming it. I'm basically numbering it according to its nomenclature. Then this is going to be 2. This is carbon 3. So basically I am looking along this line over here, this axis over here, viewing carbon number 2 in front and carbon number 3 at the back. So carbon number 2 is going to be in front, carbon 3 is going to be at the back. Okay? So carbon number 2 in front, carbon 3 at the back in there. The first thing that normally you draw, as I told you before, just make sure that the carbon chain is along the x-axis. The carbon chain is always along the vertical line. So carbon number 2 has a CH3. It's connected to a CH3. It's connected to another CH3 over here. And it does have a hydrogen. It has a hydrogen. So carbon 2 is connected to a CH3. It's connected to another CH3. And it has a hydrogen. So you go ahead and you draw that. You can put the bonds, since I did not specify which is in front and which is behind, you can put them anywhere. Now, if you want to specify and be more specific, let's go ahead and be more specific in here. Let's make the hydrogen to be in front and the CH3 to be at the back. And then I have my CH3 here to be in plane. So the CH3 in plane, I made it here. The hydrogen in front, I put it there. And the CH3 at the back, I put it over here. This is for carbon number 2. For carbon number 3, this is going to be at the back. Then I do have my 2 hydrogens. One is going to be in front. The other one is going to be behind. And then the CH3 is going to be in plane. So the CH3 in plane, one in front, and the other one is behind. This is going to be my staggered conformation in this case. Now, I cannot call this anti. Reason why? Because I have another CH3 in here. Normally, anti is whenever you have your big groups 180 degrees away from each other, yes. But I have this other CH3 over here, so this is not called an anti. I need to calculate its energy to see if it's stable or not. Now, the question says, draw all the staggered conformations and which is the least stable. To go from one staggered conformation to the other, you're going to do a rotation of 120 degrees, not 60. You do 60 when you go from a staggered to an eclipse. But to go from one staggered to another staggered, you need 2 60s. So you need 120 degrees. We fix one carbon here. I'm fixing the carbon in front. I'm rotating the one at the back. So rotating the one at the back, this CH3 is going to be 120, so it's going to be here. Remember, this is 60 and this is 60, so it's going to be 120 here. That hydrogen is going to be here, and this hydrogen is going to be on the side here. Rotating another 120, then I'm going to end up having another staggered structure. For normally we should have 3 different staggered structures for chains that are more than 4 carbons or more. We have 3 staggers and 3 eclipse. Okay, normally we have a total of 6 conformations because you do rotation around, you do a full circle rotation. This is a 360 degrees, so you should end up having 6 conformations. You cannot have 7 conformations. You cannot do 7 conformations. So, so I'm going to end up having the third staggered conformation. Now, which one is going to be the least stable in energy? I need to calculate the energy. So let's go ahead and see. With respect to this structure here, I only have a CH3 Gauche interaction. You go to the table. You go to the table. This is how I want you to write it. CH3 Gauche. And you go to this table over here. And for the CH3 Gauche, this is 0.9 kilocalories per mole. Or if you want you can report it in forms of kilojoules per mole. I believe I'm reporting it in a form of kilocalories per mole in this example. So this is going to be 0.9. Do the same thing for this over here for this staggered conformation. I have again a Gauche conformation. And for this one, I have 2 Gauche conformations. The question asks me, which one is the least stable? The least stable is the one with the most energy. This one is the most energy. So this one is the least stable. This is how you explain. In organic, when I ask you explain, you normally explain with numbers, or you explain by writing down your explanation, or you explain by writing down your reaction. Here there's no reaction, but you can easily calculate the energy of the structure. We're doing the same thing for the eclipse conformation. So once you have the stagger, I'm going to rotate. I'm going to fix one carbon which is in front. So I'm fixing the one in front. So the one in front is fixed. Okay, you can simply draw it the same for all the structures. And then for the one at the back, I am rotating it. So for the one at the back over here, I'm going to rotate it 60 degrees to go from stagger to eclipse, and then rotate the eclipse 120 every single time to get a different eclipse conformation. So rotating 60 brings from this stagger to this eclipse, and then rotating another, rotating 120 now. 120 is going to make this CH3 here. So you're going to end up having, see that fully eclipse over there? This is going to be fully eclipsed, very, very high in energy, this guy over here, because you have these types of interactions. You have the hydrogen-hydrogen eclipse. This is the torsional strain over here, corresponds to 1.4 kilocalories. You have the hydrogen CH3, no, the hydrogen-hydrogen corresponds to 1. The hydrogen CH3 corresponds to 1.4 kilocalories. And then you have the CH3 eclipse. In this case, and not just the eclipse, you have here eclipse, and you have the it's going to be the torsional, and you have the steric. So both, it's going to be torsional and steric at the same time. This is why the energy is going to be very high. The term steric, again, we defined it whenever you have 2 big groups close to each other. So if they are here having a 0 degree angle apart from each other, so this means that they align with each other, they are basically close to each other, so there is a steric strain here, and there's on top of that, because they are eclipsing each other, there is a torsional strain. So there are 2 types of strains in here. With this one, you have just the torsional strain, which is eclipsing of the bonds. So the question says which one is most stable. The one which is, draw all the eclipse conformation. The one which is the most stable is the one that has the lowest energy possible. So which one is the most stable in there? So again, the one which is the most stable is the one that has the lowest energy. And the one that has the lowest energy in this case, it's going to be, I have here 3 hydrogens. So these two are going to be the same. It's going to be a is going to be a CH3 over here. So this is going to be basically, that is going to be the lowest, this is going to be the most stable, and this is going to have the lowest energy possible, okay, compared with the 3 different eclipse conformations.